So we want to deepen our investigation of the integers mod n a little bit in section 11.5. So we've seen that the relation congruence mod n, right, so two things are going to be related to each other if they're congruent mod n. We saw previously that this is symmetric. Well, let's put reflexive first. Reflexive, symmetric, and transitive. It satisfied our three different properties, and therefore it's an equivalence relation. And because it's an equivalence relation, we can consider the equivalence classes. And we saw that these equivalence classes are going to be things like the equivalence class of 0, the equivalence class of 1, all the way up to the equivalence class of n minus 1. Because then the equivalence class of n is the same as the equivalence class of 0 because n is congruent to 0 mod n, and so forth. So I want to think about this set of equivalence classes mod n and think about sort of what math we can do on that set of equivalence classes mod n. So in order to sort of go a little bit deeper into this, let's think about a specific example. So I'm going to think about n equals 5, and we've already talked about those equivalence classes mod 5. So we have the equivalence class of 0. I'm just going to kind of write them all over the screen here. The equivalence class of 1, the equivalence class of 2, the equivalence class of 3, and the equivalence class of 4. And now I can left some space so I can actually say what those equivalence classes are, right? So I'm just going to draw them as sort of blobs in space. I know that each of these equivalence classes is a set of real numbers, and these sets form a partition of the integers. So every integer is in exactly one of these sets. So 0 is in its own equivalence class. 1 is in its own equivalence class. 2 is in its own equivalence class. 3, you can move this down a little bit. Give ourselves some space to draw its blob here, is in its own equivalence class. And then last we'll have the equivalence class of 4. And then we just kind of go around. 5 is equivalent to 0, 6 is equivalent to 1, 7 is equivalent to 2, 8 is equivalent to 3, 9 is equivalent to 4, and so forth. So I'm just going to go around and fill in a few of the different numbers here so I can think about all of those equivalence classes mod 5. So let me go ahead and do that, and then I'll come back. Okay, so I filled in basically all of the numbers between negative 20 and positive 30, just to give us some examples of what these equivalence classes look like. Now what we want to do is we want to think about doing addition and multiplication on these equivalence classes. So let's go ahead and see what that looks like on the next slide. Okay, so let's think about doing some addition or multiplication here. So let's start with some addition. Let's say I want to add 0 plus 4. Right, this is kind of a weird thing. I'm actually thinking about adding these as sets. So what I'm going to do, and we'll see why this is okay later, is I'm going to have you just look at the set containing 0, the equivalence class of 0, and pick any number in there you want. So maybe somebody's going to pick 5, someone else will pick 10, someone else will pick negative 10, and so forth. And then pick your favorite number from the set containing 4, any one you want. So maybe somebody has 5 and then they picked 4. Somebody else may have picked 15 and then negative 6. Maybe somebody else picked 20 and then negative 16. And then we'll just add those together. So you get 9. 15 minus 6 is also 9. 20 minus 16 is 4. And then we're going to just find out which set those ended up in. So the answer there is going to be the set containing 4. Okay, so that was nice, right? In the 3 examples we showed, we did end up in the same set. So let's try it a few more times. Pick a number in 1's set. Pick a number in 3's set. Whichever ones you want. Add those together. So I want to pick 6 and 8. So I get 14, and then figure out what set that's in. That was in the set containing 4 also. You can always just pick that canonical thing, right? 1 and 3, right? So maybe I try 2 and 3. So I can just think about adding 2 and 3, and that gives me 5. But I'm going to name each of my sets by that starting equivalence class. So 2 and 3 equals 0. So it turns out it doesn't matter which element you choose from that set. Anytime you pick some element from the set and add it to some other element from some other set, so I can then think about what the result is, it doesn't matter which element I've chosen, I'm always going to end up in that same set. So this operation of addition is well defined on these equivalence classes because it doesn't matter which representative you choose. So we can define it to just be the sum of those canonical representations. So I could just think of it as 1 and 3, and then I might need to reduce that because the only answers I'm going to be allowed to output are the equivalence classes 0, 1, 2, 3, and 4. Right? So I'm going to think of my set of unique equivalence classes, and I want to be able to add and multiply numbers in that set and output numbers in that set as well. So I'm defining an operation on this new set. So let's do a little bit of multiplication as well here. So if I do 0 times anything, I should just get 0 times 3 is 0. I can do 2 times, say, 4. 2 times 4 is 8, but 8 is in the same equivalence class as 3, because 8 is congruent to 3 mod 5. So I would say that that was just the equivalence class of 3. So we can think about defining this operation by picking numbers in those equivalence classes, multiplying them, and then thinking about the equivalence class of the output. So when I'm thinking about this set here, I usually define this as Z mod n. So I would call this guy Z mod 5, or you'll hear it called Z5. And it's just that set of equivalence classes. So let's start with the 0 guy there. And we can define addition and multiplication on this set. So in this case, it's actually a field. It's a special type of set because it has an addition, a multiplication, and then it also satisfies a bunch of properties between those additions and multiplications. So let's go ahead and think about what that addition and the multiplication in Z5 look like on that next slide. And then we'll actually prove that we do get this relationship so that we can choose any instance from that equivalence class, do the operations there, and then we're going to get the same thing. Okay, so let's do this addition and multiplication here. We get to make our little chart like we had when we were learning addition and multiplication the first time. So if I'm adding 0 to anything, it doesn't change it. So I can fill in that top row. Addition and multiplication are both commutative. So this is going to be symmetric about that diagonal, so I can fill in that first column as well. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5, but 5 is equivalent to 0 mod n. So we do want to remember that we shouldn't ever go any higher than 0 to 4. And then again, this should be symmetric, so I can go ahead and fill in this next column as well. All right, again, doing addition, so 2 plus 2 is 4. 2 plus 3 is 5. 5 is the same as 0. 2 plus 4 is 6. 6 is the same as 1 mod 5. And then again, we fill in that row using our symmetry. 3 plus 3 is 6. 6 is congruent to 2 mod 5. And 3 plus 4 is 7, which is congruent. Sorry, I said 2, but I meant 1. 6 and 3 and 4 is 7. 7 is the same as 2 mod 5. All right. Symmetry, 4 plus 4 is 8. 8 is the same as 3 mod 5. So then we can look at all of the nice patterns we get here, right? We're just adding 1 each time, so it's just going to increase by 1 as we go over. It has that nice cyclical pattern. Every row and every column has exactly 1 of each of the numbers. Lots of nice properties going on. So then, okay, let's go ahead and do the same thing for multiplication. So here, when I multiply anything by 0, I get 0. So my whole first row is going to be zeros. And my whole first column is going to be zeros. 1 times 1 is 1. 1 times anything is just that same thing. So I can go ahead and fill in this. And again, we have that same symmetry because the multiplication is commutative. 2 times 2 is 4. Put that in. 2 times 3 is 6. 6 is 1 mod 5. 2 times 4 is 8. 8 is 3 mod 5. Symmetry. So I'll go ahead and fill this guy in. 3 times 3 is 9. 9 is 4 mod 5. 3 times 4 is 12. 12 is 2 mod 5. Symmetry. And 4 times 4 is 16, which is just 1 mod 5. So again, I encourage you to kind of stop for a second, look at the patterns we have here. Here we have an entire row and an entire column of zeros. But if I disregard that, then the rest of my rows and columns each have a unique 1, a 2, a 3, and a 4. These multiplication and addition tables take some practice, so I definitely encourage you to maybe go back and try this one on your own, see if there's any things where you got confused. You can always kind of do it a little bit slower, right? If I'm thinking, right, 4 times 4, well, 4 times 4, that's going to be 16, so that should be the equivalence class of 16, and then I just need to think about what 16 is congruent to mod 5. So one way that you can do that is you can just start subtracting off 5 until you get a number between 0 and 5. So that would give me, again, that equivalence class of 1. So I encourage you to work through these and see if you can kind of get the patterns down. So here's the one for you to practice on. I want you to find the addition and multiplication tables, mod 4. So you should have the equivalence classes of 0, 1, 2, and 3 in this case. And then think about what all of those are multiplied together and added together. And then answer the question down here. So if you have two things that are multiplied that give you 0, does that mean that one of them has to be 0? So compare what happened mod 4 to what happened mod 5 and see if you can come up with any conjectures about that. Okay, so we wanted to show that this addition and multiplication, which we sort of defined as doing on these blobs, is well defined. So it's well defined on those equivalence classes. So what do I mean by that, right? Maybe somebody picked A as their first thing from an equivalence class, and somebody else picked an A prime, right? So I have this A is equivalent to A prime. They were in the same equivalence class, mod n. And then for the second blob, somebody picked B and somebody else picked B prime. So B was congruent to B prime mod n. And then they added those together. I want to show if we look at those equivalence classes, we actually get the same thing. And if instead of adding, they multiplied those together, that would have given us the same as well. Okay, so I want to show that it doesn't matter which item you pick from that equivalence class. If you have any item from the first equivalence class added to any item from that second equivalence class, then you're going to get the same equivalence class output and the same thing for multiplication. Anything from the first equivalence class multiplied by anything from the second equivalence class will always give us that same output. So how do we actually show that? Well, it's an if then, so I'm going to assume that A is congruent to A prime mod n and B is congruent to B prime mod n. So let's go ahead and just say what that means. It means n divides A minus A prime and n divides B minus B prime. So A minus A prime is n times some x, and B minus B prime is n times some y for x and y in the set of integers. Okay, and now I want to show that the equivalence class of A plus B is the same as the equivalence class of A prime plus B prime. So remember, we said that they're going to have the same equivalence classes if they're equivalent to each other, mod n. That's what we showed last time. So I want to try to show that a plus b and a prime plus b prime are equivalent mod n. So here's my want to show in the corner down here, which means I want to show that a plus b minus a prime plus b prime is divisible by n, so is equal to n times something. But that's the same as a minus a prime plus b minus b prime, equaling n times something, which we should be able to get from what we have. So then I'll go in here and say then a minus a prime minus b minus b prime, which is equal to, well, let's say that's equal to nx minus ny. So doing some algebra here on each side, because I do know that this is an equality, so I can work both sides. A minus b, sorry, a plus b, that should be a plus there, make that a plus. A plus b minus a prime plus b prime equals n times x plus y. So n divides a plus b minus a prime plus b prime. So a plus b is congruent to a prime plus b prime. Okay, so then for the final discussion question here, I want you to finish this proof by showing that AB, the equivalence class of A times B, is equal to the equivalence class of A times B prime. Doing the same sort of argument, and we'll talk about that in class. Okay, I do want to make a quick note about section 11.6. So in our discussion of relations so far, we've always talked about relations from one set to itself, but we can also have relations between two different sets. And that's going to be helpful to sort of think about those relations and generalize this relation definition when we go and talk about functions. So we're going to find the functions as special relations on two different sets. So if I have a relation on two different sets, a set from A to B, a relation from A to B, then that's just a subset of the Cartesian product of A and B instead of being a subset of the Cartesian product of A and A, which we had so far. So again, you're going to have something from A and something from B, and you'll just say they're related. So we'll see lots of examples of this when we talk about functions in the next chapter and in the next video.